Okay, so in earlier lecture we talked about the concept of optimization. We talked what do you mean by optimization. Then we saw the concepts like LPP and NLP, linear programming and non-linear programming problem. Then we saw that for LPP, the feasible set is a convex set. And whenever you have a convex set, things are very much nice. Like you have seen that the optimal value, where does the optimal value occur? The optimal value occurs at the corner points. So therefore, convex sets are good to play with because we have many information. Okay, so therefore LPP are good to play with, and that's why you study in your 12th. And then comes NLP. NLP means when either the objective function or one of the constraints are not linear, then we call it as a non-linear programming problem. Then further we did one more categorization of optimization, that was nothing but the constrained optimization and the unconstrained optimization problem. Okay, constrained and unconstrained optimization problem. Now how does the unconstrained looks like? So suppose you want to minimize f of x bar and your x bar belongs to Rn, and here in constrained minimum of f of x bar, where x bar belongs to C, which is a constraint set, and your C is a proper subset of Rn. Or another way to write is, I have to minimize my function f of x bar and subject to my gi's are less equal 0. Okay, so both the ways are fine. So unconstrained, where there is no restriction on your x bar, it can be anything from Rn, and that's what we saw yesterday. Then if you have an unconstrained optimization problem, how to find the optimal value? So you just take the gradient, you equate it to 0. Okay, the points where it is defined and not defined, those are called as the critical points or the stationary points. And then you take the second derivative test. That is, you take the help of the Hessian matrix of f, and you take the help of the principal minors and see whether it's a local maxima or a local minima. So that's how you tackle about the unconstrained optimization problem. Now question is how to take care of constrained optimization problem. When you have some constraints, how to take care of the constraint problem. Now, have you seen about in your engineering, have you seen Lagrange multiplier method or optimization method, Lagrange optimization method, something like that, where if you have f is a function and g is a constraint, you write grad f is some lambda times grad g. Have you seen this? I'm not saying whether you remember this or not, but have you seen this? Yes, no, or don't remember?
Yes, sir.
You have seen this. Okay. So yeah, so that's the basic thing we are going to do today as well. Okay, the some general version we are going to do. Okay. So how does a general constrained optimization problem looks like? How does in general a constrained optimization problem looks like? So it will be like minimizing the function subject to constant constraints gi of x less equal 0, where I is from 1 to up to n. So you have some n constraint and you have to minimize the function. Okay. What are your f and gi's? They are a function from Rn to R. Your f is an objective function and your gi's are the constraint functions. So this is how in general an optimization problem looks like. Okay. Now again let's come back to the convex problem. Now as I told you earlier as well, when you have convexity, things are pretty much good. So when I will call this problem, or even before that, what when you say a problem is a convex programming problem, when you say a problem is a CPP, convex programming problem, short form is CPP. Okay, LPP, NLP, IPP, CPP, these are the standard phrases or the short forms you will see. Okay, so let me call this problem as problem P. So this is my problem P. What is the problem? I have to minimize the objective function subject to the constraints gi of x less equals 0. Okay, so P is called a CPP, convex programming problem, if your f and gi's for all I, okay, all gi's are convex functions. Okay, and again you can see when the gi's are convex, the feasible set will be a convex set. Okay, so that's why it's good to play with them. Okay, I think that's easy, one can easily prove. So what is my feasible set? A feasible set will be what? X bar belongs to Rn such that your gi of x bar is less equal 0. Okay, this is my constraint set. What is given to me? Given that your gi's are convex functions. Can you recall when you call a function to be a convex function? So your gi of lambda x plus 1 minus lambda y is something times g of lambda into g of x bar plus 1 minus lambda into g of y bar. What is the sign? Less equal or greater equal? What is the sign? Less equal or greater equal for convex functions? You have seen this in your earlier lectures. When you call a function to be a convex function, if f of lambda x plus 1 minus lambda y is something less equal or greater equal lambda f of x plus 1 minus lambda f of y.
Less equal.
Less equal.
Yes, it has to be less equal. So all my gi's are satisfying this condition. So when your constraint set or when your constraint functions are convex function, then my claim is your feasible set is a convex set. When you call a set to be a convex set, so let's try to prove this. What is my claim? My claim is S is a convex set. So that means what? Let x bar comma y bar belongs to S. That means what? Your x bar and y bar satisfies all the constraint in equations. Gi of x bar is less equal 0. Gi of y bar is less equal 0 for all I. What is our claim? When you call something to be a convex set, if you take two elements from that set, then the segment joining those 2 points. How do you write mathematically? The segment joining those 2 points is represented by this equation. Then the segment should also lie in the set F. Okay. So then we say the set is a convex set. So that means what I want to prove? We want to prove that gi of lambda x bar plus 1 minus lambda into y bar is less equal 0. This is what we want to prove. Is the proof easy? What is given to us? Gi's are convex functions. So if we start with the left hand side, gi of lambda x bar plus 1 minus lambda into y bar, by definition of convexity, this is less equal lambda times gi of x bar plus 1 minus lambda into gi times y bar. Is this less equal 0? So conclude. Is this less equal 0? See what is given to you, and is this less equal 0? Your lambda is positive and 1 minus lambda is also positive. Both are greater equal 0. Okay, because lambda is from 0 to 1. So they both are positive quantity. What about gi of x bar and gi of y bar? Are they positive or negative?
Negative.
Negative, yes, because if I call this as star, then by star, this is lambda into 0 plus 1 minus lambda into 0. So therefore this whole quantity is less equal 0. So therefore, your lambda x bar plus 1 minus lambda y bar, this segment also satisfies the constraint functions. Therefore, this belongs to S. And this is true for all I. Okay. So when your constraint functions or your GIs are convex functions, then your feasible set is always a convex set. Okay, then your feasible set is always a convex set. So just write down this phrase for your later understanding. So when the constraints are convex, then the feasible set is always a convex set. And therefore, if you recall in LPP, your constraint functions are always linear functions, and linear functions are always convex functions. And therefore, its feasible set is a convex set. Okay. So when you have a CPP, CPP means what? Your F is convex, your GIs are convex. So in CPP, so therefore in CPP, feasible set is always a convex set. Feasible set is always a convex set. Okay. In therefore, in particular, feasible set of an LPP is a convex set. Because in LPP, your F and GIs all are linear, and linear functions are always convex. Okay. Okay, good. So that's about CPP, convex programming problem. So whenever, so when you call a problem P a convex programming problem, so if you have a problem of the form minimum of f of x bar and your GIs of x bar are less equal 0, if you have a problem of this form and your f and GIs are convex, then we call the problem P to be a convex programming problem. But now suppose instead of this P, see what I want to say now is it is sufficient to concentrate on this problem. We can without loss of generality, we can concentrate on such type of problems. Why so? Because if you have a problem which is not of this form, then वो कौन से form का होगा? Then what are the possible form it can have? So see, the first form it can have is I have to minimize f of x bar and my GIs are less equal 0. So when I call this to be a CPP, when my f is convex and my GIs are convex, then I will call this to be a CPP. Suppose you have a problem of this form. I want to maximize f of x and my GIs are less equal 0. Now when I will call this problem to be a CPP, so you can see in both the scenarios my GIs are less equal 0, so my GIs has to be convex. What should be the condition on f so that I will call this to be a convex programming problem? See, if f is convex, what can you say about minus f? Is it convex or concave? If f is convex, what can you say about minus f? You need to brush up these things, okay? If f is convex, then minus f is always concave. So here, maximizing f of x is same as minimizing minus f of x. Okay, so if I'm saying f is concave, then minus f becomes convex. Okay, so this will imply that your minus f is convex and maximizing f of x is equivalent to solve minimizing of minus f of x. Okay, so suppose if you have a problem which says maximize f of x and GIs are less equal 0. So when do you call the problem P2? When I will call P2 a convex programming problem if your f is concave and GIs are convex. When I will call P1 to be CPP if your f is convex and GIs are convex. Okay. Now let me take P3. Now you tell me, what do you think? What should be the condition? If I have a programming problem P3, which says minimizing of f of x and gi of x are greater or equal 0, when I will call this a CPP? If any wild guess?
If f of x is convex and gi is concave.
Perfect. When f is convex and gi's are concave, then I will call such a programming problem to be a convex programming problem. Okay. And the last case comes out to be P4. I have to maximize f of x, and my gi's are also greater or equal 0. So I will call this problem to be a CPP if my f and gi's all are concave functions. Okay. So these are the classification of problems in CPP. Okay. So we will usually concentrate on P1, because if you have other types, then the same thing can be done. So it's okay. So we will only, whenever you see a problem in book also, no, they will many times they will say consider this problem, because then other cases are automatically gets covered. So if you have minimizing of f of x and gi's are less equal 0, then you call it as a CPP if f and gi's all are convex. Okay, and LPP are always a CPP. Okay, let's take an example. If I suppose if I want to minimize f of x bar is equal to 7x1 plus say 3x2, subject to, suppose if I take x1 square plus x2 square less equal 1, and if I say x1 square is less equal x2, where my x1 my x2 is greater or equal 0, suppose if I say, and my x can be, yeah, x1 can be anything. Let me keep this form, or let us keep the thing simple. X1 is from, or let's take x1 to also be greater or equal 0. Okay, x1 and x2 are greater or equal 0. I want to check whether, so you can see that this is not a LPP. Is this an LPP? Answer is no, because you can see the constraints are not linear. So this is not an LPP. So this is an NLP. Is this NLP a CPP? Is it a CPP? That's what the question is. So you want to check whether f and gi's are convex or not. Okay. So is your f a convex function? Is your f a convex function?
Yes, sir.
Yes. Why? Because it's a linear function. Okay. So your f of x bar is nothing but 7x1 plus 3x2. It's a linear function. Therefore, it's a convex function. Okay. What is your g1 of x? G1 of x bar is nothing but x1 square plus x2 square minus 1. Okay, because we say g1 of x is less equal 0, right? So this is my g1 of x. Is this a convex set? Okay, let us go by the diagram. What is this? It is nothing but the points on the circle and inside the circle. So obviously you can see, you take any point in this set, the segment joining those 2 points will again lie in the set. So this is again a convex set. What about g2? What is g2 of x? X1 square minus x2. What is this? So x1 square equal to x2 is nothing but a, so like y equal to x square. It's a parabola. Interior of parabola or exterior of parabola? What do you think? Your x square, your y is greater or equal x square. What do you think? Interior of parabola or the exterior of parabola? Just take a point 0, 1. Does 0, 1 get satisfied here? X1 is 0 and x2 is 1. Will 0, 1 will be satisfied? Pradnya, what do you think? Will 0, 1 will be satisfied? Abhishek? Vinay? Ashu? No one? Will 0, 1 will be satisfied? Will 0, 1 will satisfy this inequation x1 square less equal x2?
Yes, sir, it will.
Pankar. So 0, 1 because your 0 square is obviously less equal 1, so the interior of the parabola. Again, you can see this is a convex set because if you take any 2 points, the segment is within the parabola. So therefore, this is a convex set. What is my G3 of x? My x2 is greater or equal 0 means what? My minus x2 is less equal 0. So my G3 of x is minus x2 and my G4 of x is minus x1 because x1 is greater or equal 0 implies minus x1 is less equal 0. Okay, so we always keep our constraints to be less equal 0. Okay, so my G3 of x is minus x2 and this is minus x1, which are again the convex. So all GIs are convex, so F is convex, so therefore yes, this is a convex programming problem.
Excuse me, sir.
Huh?
Sir, can it when we say about convexity, that the function, the line joining the 2 points on the function needs to be above the function, above the graph of function.
Yes.
So
That is for the graph,
in
but
case
this is not the graph of a function circle.
no, sir, I was a little confused about the definition of convexity. So
Okay.
in case of straight line, can it be said that the 2 points joining, any 2 points joining on the curve needs to be above or on the curve?
Above or on the curve. So there are two things: convex functions and convex sets. So convex function means you take any 2 points, then the segment should be above the or on the curve. Okay, and so
Yes,
for therefore the straight lines, they are always convex as well as concave. Some people, some author also categorize this further as strictly convex or only convex. So if someone is talking about strictly convex sets, then line won't be a convex set. Okay, but in our case, we'll only talk about convexity. We will not go into strictly convexity. So therefore, your line is a convex set or convex function.
okay, sir.
Clear?
Yes, sir.
Do you want me to elaborate any other point?
No, sir. Thank you.
Okay, fine. Okay, good. Now see, what I want to tell you over here is, so this is a CPP which we found because this was a line and then we just drew this set. Suppose if you have a very bad equation and you don't know what is the set or what is the graph is looking like. In that scenario, what to do? So you must have seen this earlier. Let me just recall this. So if you want to check whether some function is a convex function or not, if you want to check whether f is convex or not, you simply find the Hessian of that matrix. If that Hessian is positive definite matrix, then we call that function to be a convex function. Have you seen this result in earlier session when you studied convexity? Okay, anyways, even if you haven't seen, you can just keep in mind. Okay, so if you want to check whether a function is convex or not, you simply find the Hessian. It has to be positive definite or positive semi-definite. Okay, do you remember when you call a matrix to positive definite? When x transpose AX is greater or equal 0, then I will call this as a positive semi, then A is called as a positive semi-definite matrix. When x transpose AX is strictly greater than 0, it is called as a positive definite matrix. When this is strictly less than 0, then A is called as what? When x transpose AX is strictly less than 0, then it is called as negative definite matrix. And when x transpose AX is less equal 0, then it is negative semi-definite matrix. Okay. one can relate this to eigenvalues. Do you know the conditions? When all the eigenvalues of that matrix are greater or equal 0, then it becomes positive semi-definite. If all the lambdas are strictly greater than 0, is equivalent to say it is positive definite. If all eigenvalues are strictly less than 0, then negative definite, and less equal 0 are this. So these are equivalent conditions. To say something is positive definite, so this is a definition. These are the equivalent conditions. Sometimes it's not always easy to check using the definition, so we take the help of eigenvalues. Okay, and then you can also take the help of the principal minors. You can also take the help of principal minors. When all the principal minors are greater or equal 0, then you call this as a positive semi-definite matrix. Have you seen these conditions earlier? I hope so.
Yes, sir.
Okay, so
Yes,
just
sir.
revise the things. Okay, so to check something is convex is same as to say whether the gradient is positive semi-definite or not. So in this case, what was the function? What function I wrote earlier? I wrote 7x1 plus 3x2. Just find the Hessian. इसका Hessian क्या होगा? Suppose I don't know whether this is convex or not. Find the Hessian. F with respect to x1 is 7. F with respect to x2 is 3. And if I take that second order derivative, everything is 0. So obviously, if I call this as my matrix A, obviously my x transpose AX is always 0, which is always greater or equal 0. Okay, so therefore this is a convex function. What about your G1? Your G1 was x1 square plus x2 square minus 1. What is Hessian of G? So when you with respect to G with respect to x1 is 2x1, G with respect to x2 is 2x2. So when you take the second derivative, this will be 2, 2, and this will be 0, 0. So you can see again, it's positive, diagonal, everything is positive. So you can see that if I call this as B, then x transpose Bx is greater or equal 0. If you can't see this, it's okay. What are the eigenvalues? Since it's a diagonal matrix, they are the diagonal entries which is greater than 0. So therefore your G is also convex set. Okay. Similarly, you try for G3, G4 and G5. Sorry, G2, G3 and G4. Okay. So if you don't know whether something is convex or not, don't worry. Simply find the Hessian, check whether they are positive definite or not. If yes, great, they are convex. If not, it's not convex. Is this clear how to use Hessian? Can I get thumbs up if it's clear? Okay, good. So people, okay, you can raise the hand or you can just give me a thumbs up. Okay, cool, good. Okay, what about this example? Let's take one more so that I can just see more thumbs up. That's all. Suppose if I give you, I want to maximize the function 4x1 minus 5x2 subject to x1 square plus x2 square less equal 4. My x1, x2 less equal 1 and my x1 and x2 are positive. Is this a CPP? Let's try to check it out. Is your f a concave? Because I want to maximize. So is your f a concave function? Yes, it's linear, so it's concave. What about G? Let's take G2 directly. Let me jump to G2. It is x1, x2 minus 1. Can anyone tell me what is the gradient of G2? What is the first row and what is the second row? Anybody? What is G2 with respect to x1? It is x2. What is G2 with respect to x2? It is x1. And when I take the second derivative, this becomes 0, 0. And this is 1, 1. And as you can see, the principal minor, or you can say the determinant principal minor is all are not positive. So therefore, this is not positive definite. Therefore, this is not convex. G2 is not a convex function. Okay, or you can find the eigenvalues as well. The eigenvalues will come out to be plus minus 1. So they're not all are positive. All has to be positive. Okay, so you can see that the eigenvalues will come out to be plus minus 1. Not all are positive. Therefore, again, this is not a convex function. So this is not a CPP. Is this example clear? Can I get a thumbs up if it's clear? Okay, good. Now, in NLP, we talked about CPP. Okay, convex programming problem. When you call an NLP to be a CPP, that's what we have seen. Now, there is one particular type of problem which occurs a lot. Okay, and that's why people study them as well. Quadratic programming problem. Okay, so if you have a problem, say minimizing f of x bar subject to the constraints gi's for I equal to 1 to n. When I will call this problem P to be a QPP, if your f is quadratic, your f is a quadratic, that means the highest degree is 2, and your gi's are linear. Gi's are linear. If you have a problem of this form, obviously it's NLP because degree of f is not 1. Okay, because your f is not linear. So, but f is quadratic, so it's a NLP, but your gi's are linear. Then we call such a problem to be a QPP. Okay, so let me take an example. Let me suppose I want to minimize a function 4x1 square minus 2x1 x2 plus 9x2 square plus 6x1 plus 10x2 subject to 3x1 plus 7x2 less equal 1, and suppose GS has to be linear, no? So x1 plus 6x2 less equal 10, and where x1 and x2 are positive. Now, as you can see, all the four constraints G1, G2, G3, G4, all the four constraints are linear. Therefore, and your f is quadratic. Therefore, this is a QPP. It's an NLP. In NLP, it is particularly a QPP, quadratic programming problem. Okay. Now, why people study quadratic programming problem? Because it's easy to play with. Why it is easy to play with? Because one can observe that one can always write down that problem in a nice way. And few more things are there that I will tell you. You can always write down your problem in this way: half C transpose x bar plus half x bar transpose qx subject to a x bar less equal b, your x bar is greater equal 0. Where your, what is your C and X? They are vectors in Rn. Your B is a vector in Rm. Your A is a m cross n matrix. Your Q is a symmetric matrix of order n. Your Q is a symmetric matrix of order n. You can always write down your QPP in this form. One can always write a QPP in this form. Now let us try to write the earlier problem in this form. Can you write, see, this is x transpose q x bar, matlab this has to be a quadratic term. This will contain the quadratic term and this will contain the linear term. Okay, so if I want to do that way, so how will I do? I can observe that one can see that this is 6 and 10. So let me take a different color. You can write this as 6 and 10 as a row vector, and you multiply by the column vector x1, x2. So this is nothing but the last two terms. What about the first three terms? You can write down this as, you write your x1 square ka coefficient here, you write down x2 square ka coefficient here, and you divide by 2 the coefficient of x1, x2. Okay, then if I do this, x1, x2 and x1, x2, you can just multiply this row vector into this matrix into the column vector. When I do this multiplication, you can do this at home later on. You just listen and just convince yourself that when I multiply this, I get this thing. Okay, coefficient of x1 square, coefficient of x2 square, and you divide the coefficient of x1 and x2 by 2. If I do this, if I multiply x transpose this matrix into x, then I will get this matrix. Okay, so what I was saying was, so in this case, what is your C vector? 6, 10. Your C vector is nothing but 6, 10. Your Q matrix is nothing but 8 minus 2 minus 2, 18. Why I multiplied this matrix Q by 2? Because here I have written half into Q. Okay, so this half I'm doing here. That's why I multiplied this whole thing by 2. So I have to multiply divide by 2, so that when I put it over here, when I divide by 2, I should get this as an answer. Okay, so that's why multiplied by 2. What is the matrix A? It is nothing but the coefficient matrix 3, 7, 1, 6. This you already know, 3, 7, 1, 6. Your B vector is the right hand side of the inequality, which is 1 and 10. And your x bar is greater equal 0 vector. Yes, so one can always write a QPP into this form. One can always write QPP in this form. Okay, so can someone just write down this problem into that form? 3x1 square plus x1 x2 plus 7x2 square minus 4x1 plus 3x2. Can anyone tell me what is my C and what is my Q? Constraints, let it be. Constraints are linear, so linear is easy to write. Can you tell me what will be the C and the Q, C vector and Q matrix, such that your f of x bar is nothing but half x bar transpose qx plus C transpose x bar. Okay, C vector is easy to tell. What is the C vector? X bar is x1, x2. So from here, what is the C vector?
Minus
4,
4.
3.
Perfect, minus 4, 3. Now what is the matrix Q?
3, 1 by 2, 1 by 2, 7.
3, 1 by 2, 1 by 2, 7. But now here I'm writing half into Q. So therefore I have to multiply. So see, if you do this, no,
Yeah, 2.
yeah, so I have to multiply this by 2. So if I do X transpose this matrix into X, no, I will get this thing. But here I'm writing half into Q. I will tell you the reason why I'm writing half into Q after some time. But I'm writing half into Q, so I have to make sure I multiply this by 2. Therefore, this is nothing but my Q is actually 6, 1, 1 and 14. Okay, so this is my Q. Make sure you multiply by 2. Is this clear? Can you just give me thumbs up or raise your hand if this is clear? How did I write the Q matrix? Okay, good. I can see 4, 5 hands. Okay, good. So now, and see, constraints are linear. उसमें कोई problem नहीं है. Why this works? Sorry. Why I'm saying why you multiply here? Why you divide by 2? Why I'm doing this multiplication? Because can someone just find the Hessian of the matrix? Can someone just tell me what is the Hessian of this matrix? Everyone know what is Hessian? Fx1 x1, Fx1 x2, Fx2 x1, and Fx2 x2. What is the answer? Take a moment and tell me what you are getting.
Sir, same gating, sir.
Same.
As
Anybody else got the same answer?
Yes, sir.
Okay, good. So actually your Hessian actually comes out to be the Q matrix, provided you because of this factor half. Okay. So actually, if I don't write this half no, then your Hessian is half times that, but then you multiply divide by 2 so that it becomes equal to. That's the reason you will see many author writes QPP in this form. And many people usually they think, why they're writing half, what is the use? Well, the answer is because when you take the Hessian and if you write in this form, it is actually equal to the Q matrix. Okay, and this helps me to answer my next question, which is nothing but when a QPP is a CPP. When you call something to be CPP, if your F is convex and all GIs are convex, then I call such a problem to be a CPP. Now, if you have a QPP, that means your F is a quadratic and GIs are linear, then when I will call that as a CPP. Okay, so you have QPP. That means you have F, which is nothing but C transpose X plus X transpose half X transpose QX. And your GIs are less equal 0, which are linear. Your GIs are linear. So since GIs are linear, so therefore they are convex. So when your F will be convex, this will be a CPP. So whenever you're, so I'm not worried about GIs because in QPP my GIs are linear and therefore they are always convex. So I'm not worried about GIs. I'm worried about F. When my F is convex, great, my QPP will become a CPP. So is there any nice way to check whether this QPP is a CPP? Answer is yes. And for that, the answer is a nice theorem. When your Q, you know it's a symmetric matrix. If you have observed carefully, your Q is a symmetric matrix. Your A is equal to A transpose. So your Q, which is a symmetric matrix, when your Q is symmetric, positive, semi-definite matrix, then we say that it's a CPP. Okay, your Q is nothing but Hessian of F. So whenever you have a QPP, you simply find the Hessian of F. If it's a symmetric and positive semi-definite, say I already told you when to check a function is convex, you simply find the Hessian. If the Hessian is positive semi-definite matrix, great. Okay, but in QPP, when your Hessian comes out to be a symmetric Hessian or Q, when your Hessian or the matrix Q is a symmetric positive semi-definite, then we call QPP to be a convex CPP. Okay, so whenever you have a QPP, your GIs are linear, so they are convex, so no need to worry about GIs. You have to only concentrate on F. Either write your F in this form, which I wrote over here, and just see whether your Q is symmetric positive semi-definite or not. Or if you don't want to write in this form, you simply find the Hessian of F. If the Hessian of F is positive symmetric semi-definite, then your QPP is a CPP. Okay. Now if I go to the earlier example, is this QPP a CPP? Your Q is a symmetric matrix. Is it a positive definite matrix? Whether the principal minors are positive, what is my delta 1? It is 6. What is my delta 2? It is a determinant of this matrix. What is the determinant of this matrix? Is it positive or negative?
Positive.
Positive. So all the principal minors are positive. Therefore, your Q is already symmetric. So therefore, this is a CPP. This QPP is a CPP. Okay, so that's why this convexity is used a lot in optimization, and Hessian matrices, partial derivatives are used a lot. Okay, so many times people ask you whether the given QPP is a CPP or not, and answer is you simply find the Hessian. Well, the proof is also nice, but okay, I will do half of the proof and half of the proof I will give you as a homework. Okay, so what is the proof? What is the question? If your Q is a symmetric positive semi-definite matrix, then your QPP is a CPP. Okay, and to prove this fact, I will need one lemma, and that lemma is, what is the lemma? If you have a matrix A, which is symmetric positive semi-definite matrix, then X transpose AY is less equal half X transpose AX plus Y transpose AY. Where what is X and Y? X and Y, they are vector in Rn. So if you have a positive semi-definite matrix, then this inequality always hold. Okay, let's try to prove this. Okay, so let X bar comma Y bar belongs to Rn. So this implies your X bar minus Y bar is also an element of Rn. Now when you call something to be positive semi-definite, if your Z transpose AZ is greater or equal 0 for all Z in Rn. So take Z equal to X bar minus Y bar. So if I take X bar minus Y bar transpose A, X bar minus Y bar, then that is greater or equal 0. I will simply expand this. What will I get? I get X bar transpose AX bar minus Y bar transpose AX bar plus X bar transpose minus X bar transpose Y and plus Y bar transpose AY. I have simply multiplied. Okay, I have not done anything new. I have simply took the transpose inside and I have simply multiplied. This is what I have. Now if you see the proof, I need this factor, I need this factor. So I have to play with one of the factor. Okay, I have to play with one of the factor. Now question is with which factor I will play. Now if you observe this quantity, Y bar transpose AX bar, is this a number? Is this a real number? That's what the question is. Is this a real number? What is the order of Y transpose? See, your X bar is nothing but n cross 1 vector. Your Y transpose is 1 cross n because your Y bar is n cross 1. So Y bar transpose is 1 cross n. And what is your A matrix? It's a matrix of order n cross n. So when I multiply first two, I will get the matrix of order 1 cross n. And when I multiply this and the last vector, I will get 1 cross 1, which is nothing but a real number. So therefore this quantity Y transpose AX is a real number. Don't write down the proof, just understand. Okay. So Y transpose AX is a real number. So its transpose is the same thing, because if you take a transpose of a real number, you get the same answer. But what is this? This is X bar transpose, A transpose, Y bar transpose, which is Y bar only. So this is what I have. Okay. So for my A is symmetric matrix. So this is what I get. So if I substitute this star in the given equation, in this equation, so what is my Y bar transpose AX bar? It is X transpose AY bar. Okay. So both the things are same. That's what I proved. Both the things are same. So this is nothing but minus 2 times. Since both of them are same, minus minus is minus 2 times. So therefore I have x bar transpose ax bar plus y bar transpose ay bar is greater equal 2 times x bar transpose ay bar, and therefore your x bar transpose ay bar is less equal half times the required quantity. Okay, so this is what the proof is. Very simple. Simply apply the positive definite definition to the vector x minus y bar, and simply use the fact that y transpose ax is a real number, and therefore it is equal to its transpose, and therefore you have the answer. Okay, and now you want to prove that, and now let's come to the main theorem. I will need this lemma. Okay, so if your Q is symmetric, positive, semi-definite matrix, then your QPP is a CPP. Okay, so that's what I want to prove now. So what is your F? It is nothing but C transpose X bar plus half X bar transpose QX. Now my Q is positive semi-definite, symmetric, so I can use this lemma. Okay, I have to use this lemma somehow. Okay, now what I want to prove that your F is a convex function. Okay, what is my claim? So I will give you this homework, but let me just give you a hint. F is a convex function. That means I want to prove F of lambda x bar plus 1 minus lambda into y bar is less equal lambda into f of x bar plus 1 minus lambda into f of y bar. This is what we want to prove. So we start with the left hand side. F of lambda x bar plus 1 minus lambda into y bar. But what is this? This is C transpose. What is our function? This. So f of this is nothing but C transpose into lambda x bar plus 1 minus lambda into y bar, half into x transpose means lambda x bar plus 1 minus lambda y bar transpose q into again the same thing. And now you will realize that why I'm giving you this as a homework. Now you have to take the transpose inside and multiply this complete thing, use this fact somewhere, and you get the and you will get the answer. Or actually what you do is to show, or let me tell you in a much more different way. Let me tell you a different way. To show this thing, you do this way. This will be much more easier. I have to show that minus lambda times f of x bar plus 1 minus lambda into f of y bar less equals 0. This is what I want to show. You start with the left hand side. Put this, what is f of this? It is C transpose into this x plus half into this transpose qx plus again apply f of x over here. C transpose x bar plus half x transpose qx. What is f of y bar? C transpose y bar plus half y transpose qy bar. Use, multiply everything inside. Use this lemma to prove that your LHS is less equal 0. Okay, so that's the hint to prove that a QPP is a CPP. So just prove this at home, and you can ask me tomorrow if you get stuck. Okay, so suppose if I ask you, can you just, so suppose if I give you subject to x1 plus x2 less equal 1, x2 plus x3 less equal 4, and your xi's are greater or equal 0. Question is this QPP a CPP? Okay, so no need to go for GIs because they are linear, so they are convex. I want to check whether the F is convex or not. So to check F is convex, simply check whether your Q is symmetric, positive, semi-definite. If you don't want to find Q, you simply find the Hessian of F and check whether the Hessian of F is symmetric, positive, definite or not. Okay, so once you find the Hessian, you have a 3 cross 3 matrix. Find all principal minors. If all are greater or equal 0, great. Okay, if not, then yeah, then it's not convex. Okay, so that's what the classification for today's session is. So we saw what is the NLP, what is QPP, what is CPP, and why CPP is important. In next lecture, we will see how to solve the problems. Okay, so there is some nice conditions called as KKT conditions, and there is a method called as a Newton method, steepest descent method. Those are the things that we will see that helps you to find the solution of a convex programming problem. Okay, again, convex programming problem are easy to solve. That's why people concentrate on CPP, and that's what we are going to see in our next lecture. So yeah. So yeah, it should be 2. Let us take x2 x3. It has to be x2 x3.